Hi, I'm Miles Parker. I'm project lead for the Eclipse Agent Modeling Project and also founder of Metascape. At Metascape, we do agent-based model consulting and we develop agent-based modeling tools. In the last set of screencasts, we looked at why we might want to do agent-based modeling, and in this one we'll look at how we can do it with a close look at an epidemic model. Okay, so we'll start off assuming that we have a new workspace and we've just installed the agent modeling platform with all the other components. And we're going to go over to the agent modeling perspective, which will set up our environment with a lot of nice standard tools for doing the agent-based modeling. Everything will be close at hand. So we'll create a new Escape project here, and let's call this Epidemic Demo. And this will create the project, and then suppose a colleague, myself in this case, has sent the latest and greatest version of this epidemic model. So what we can do is we could just drag that model in, and we'll see down here that the model is getting built in real time. And the user really doesn't have to worry about this process, but in the background we've created all of these Java classes, generated all these Java classes from the model. What we're really interested in is the model itself. And so let's open that up and see what it looks like. So at the first level we have the epidemic itself, which is sort of the enclosing context for this particular model. And you could imagine that being, say, a region or a country or whatever, something that's wrapping up the individuals within the model. So if we dig down in here a little bit, we see that it is made up of individuals and locations, and we have a city here, and the city is simply a 2D grid. I'm going to bring up a properties view here so that we can see the detailed information about these. So we can see that it's a 2D grid in a Euclidean space. That really, we don't need to worry about that right now, but it's a 40 by 100 grid. And let's look at individuals and see what we define there. So there are lots of different pieces here that we might be interested in. The most important is the status, and this is just a set of values that an agent can have. And just as we saw with the equation-based model, we're interested in these different states that an agent will move through. And so here we have susceptible. We have two kinds of infectious. One is what the other model referred to as exposed. Here we're calling it asymptomatic infectious, and we have symptomatic infectious, and then we have recovered, and unfortunately, in some disease progression, some people will die. And then we'll see we have some kinds of outcomes, and we have contact transmission probability, and we'll see how that works. If we go up to the next level up, which is again the epidemic level, we can see a whole bunch of attributes. And for those familiar with doing any kind of experimental modeling, your models have parameters, and these are the parameters. An interesting aspect of this is that the parameters at the enclosing level of context or scale become what we use to create the attributes at the next level down. And in fact, if, for example, we were doing a model of say organ systems within individuals, you would imagine that the attributes for an individual might provide the parameterizations for those contained organ systems, for example. So agents have a number of different attributes. Those are the properties we discussed in the previous screencast. And they have a number of behaviors, actions in this case, that they can take. And so this first rule is telling the agent to go to some location, any location on the map, as an initialization rule. So that should happen once and only once for each model. The movement rule will tell the agent to take a random walk through space. Initialized state, which we'll look at, is where we define the individual's infection status at the beginning of the model. Transmission is how the agent can infect others. Progression will track the actual progression, of course, of the disease through all of those stages that we just saw. And here we're going to look at what happens after initial exposure. Let's look at how we define these behaviors in depth, and we'll do that using the Metascape visual behavior editor. And so let's just look at the initialize location rule. This is one of the simplest things that the agent's going to do. So it's an initial rule, which means that we execute it once and only once at the start of each run. And what we do is we are an individual within a city, and we're looking for a location within the city to move to. And so we have the select action, and then we have a query, and the only thing we're interested in is that that space be available. If we find a space that's available, then we move from our current, well, we don't have a location, but we move from outside of the space into the city location. For a more complex example, let's look at what we might want to do in terms of setting up the agent initial state. So there's two things that might happen here. Some subset of the population is going to be infected at the beginning of the run. So what we'll do is we'll draw, do a random draw, and there are many different functions that we have here. In this case, it's this random unit value. Next, we'll see that if that value is less than some probability of initial infection. If we went down to the individual level here, we can see that the default value for that is 0.05. Okay, so moving back up to this rule. Okay, so at the next level, if that draw was below some value, below that value, then we set the status to exposed. On the other side here, we have some probability of transmission. And this is a really important point. As we discussed earlier, at the containing level, the epidemic level, we've defined a minimum contact transmission probability, which the default value is 0.08 for, and max contact transmission probability, which is 0.16. So if we go up here, and of course those can be parameterized in any way, as we'll demonstrate in later screencasts. But we actually set this on individual contact transmission probability. What that means is that those values, min and max contact transmission probability at the group level, are not drawn each time that an individual has a contact with somebody. And instead, they're sticky. Each individual has a different contact transmission probability, and that represents the sense that individuals have different proclivities, different habits in terms of hand washing. Maybe their health status is different in terms of their likelihood of transmitting a virus or whatever. The point is that we want to be able to represent that heterogeneity, and so that's how we do it. We'll look briefly at the two important behaviors here. The first is how we actually transmit. And so here we start out with a rule. A rule fires every period of the model. And what we're checking to see is if we're either asymptomatic or symptomatic. And if either of those are true, that's what this union means, then we're going to select an individual that's a neighbor. And if that neighbor is susceptible, we're going to do a random draw. We're going to check that that value is less than this contact transmission probability here that we set earlier. And if that's the case, then we're going to set this neighbor's exposure status, set their status to exposed. This has been a demonstration of the basic setup for how you would design a model like this. And in the next screencast, we'll actually run the model.